Recording has started, time for class. And once again, when we're in class, I want your cameras on. I want to see you as well as you seeing me. So back to electronics. A week ago, you programmed. Now we're up to the all-important design of electronics. And then in 2 weeks, we'll produce electronics. So there's two parts to this class. One is going to be introduction to the components we're using. And then the second part will be the software we use to design the circuits. You're going to design a development board around a microcontroller that you'll make in 2 weeks. And so here's one example is Adrian, Saturday host, designed a Fab Shao. So it starts with the Shao, and then it adds interfaces to many different sort of protocols. And then with the Fab Shao, he goes on and has examples of connecting it to all sorts of devices that we'll be covering in the coming weeks. So I recommend just scrolling through this page to get a sense of all the different things he can interface to. Now, you can design the circuit, but normally circuit design itself, it's creative, but not overtly artistic, but you don't need to be limited to boring boards. So the next example for inspiration was she made me as a circuit. You can design fun, interesting circuit boards. And then the third example was an impressive one. This was a student who was a good programmer. And rather than just using the software I told him about, he actually wrote software to anneal his design. So he wrote this really interesting program to make these beautiful circuits. So those are some examples for inspiration. And once again, I see lots of cameras off. If you're in class, I want your camera on. I want to see you as well as you seeing me. The body language is a very important part of the class. It doesn't work to teach the class to a bunch of flat windows. I want to see people. Okay, so lots to cover. Each week, the top of the page is linked to inventory. Here's the electronic inventory in the lab. And so we're going to start a tour through that. Now, I'm not going to talk about the physics, but this is a class I teach on that explains the physics of what's going on in these devices, if you want to know more. But we'll start right in. So we use wire. We don't, in the inventory, have separate reels of wire. This is very handy. This is a ribbon cable. And so it peels apart. So you can use it as a ribbon to have many wires going to the same place, or you can peel off individual wires. And then we have connectors I'll talk about that connect to the ribbon. Wire is specified by AWG, and so that's 28 AWG. And if you search for wire AWG versus current, you'll find all sorts of versions of tables that tell you the wire gauge versus the current that you can handle. So more current needs a fatter wire. So that's what we use for hookup. Then connectors are surprisingly important. If you have, for example, a module and you want to be able to plug it in, we need to be able to attach and detach. So we use connectors to connect wires to boards. when they need to be removable as opposed to permanent. And this is a special kind of connector. This is called IDC, which means insulation displacing component. And you'll see these little sharp fingers here. And so what you do is you put the ribbon cable in it, and then you squish the top. You can use a vise like this to put the connector in here with the ribbon, and then you compress it. And then when you do that, the fingers push into the ribbon, cut through the insulation, and contact the wire when it's pushed all the way down. And so what that lets you do is terminate multiple wires at the same time. You don't have to connect each one separately. You just push it in and squish it, and now you have a connector connected to all the wires. We use buttons to interact. Here's a classic button. This is a push button. It's normally open, and then when you push the button, the two sides of it get connected to close it. We use switches. So this is a switch. Let's see, let's go back to here. The button is normally open, and when you push it, you connect the two sides. The switch can be connected to one of two positions, and then it stays where you leave it. And so this could be an on-off switch or a configuration. And as a reminder, all of these are surface mount rather than through-hole components. So there's a switch. This is a resistor. So in America, we draw resistors like that. In Europe, often they're drawn like that. And what a resistor does is I equals V over R. So a resistor has current flowing through it. Think about this as think about water flowing in a tube, and that's how much water is flowing. And then there's a voltage drop across it. And you can think about that as how steep it is, how much gravity is pushing the water through the tube. And then the resistance is how difficult it is. Think about that as like an orifice that limits how much water can flow. And so a common use we have for a resistor is for current limiting LEDs. And I'll talk about that in just a few minutes. So the resistor is specified by the package. And so this is a 1206 package. That's in thousandths of an inch, so 12,000 by 6,000. That's the size. It's specified by how much power it can handle. This one is a 1/4 watt. Specified by the amount of resistance, and then it's specified by the tolerance, the accuracy. 1206 are fairly large resistors, physically, the package size. The reason we do that is when we machine our circuit boards, a standard size for the end mill we use is 1/64th. A 1/64th end mill, sorry, I didn't draw that well. If you want to make a trace, a wire on the circuit board, and then you're machining it with the 1/64th inch end mill, that fits underneath the size of the package for a 1206 resistor, meaning you can send a wire underneath the resistor. There are much smaller size packages And so we often use 06, 03s, and you can go down to 01, 005. That's like a tiny dot. So they come in a wide range of sizes. Most commonly for Fab Academy, we use this size that's pretty easy to solder and easy for routing. So that's a resistor. Then a capacitor, we draw like that. And in a capacitor, C equals Q over V. So V is the voltage between the two sides of it. And again, in the analogy with flowing water, that's how steep the pipe is. And then there's charge. And I'm going to add a note to my notes. There's charge on it, and Q is the amount of charge stored. So again, with the water analogy, think about it as you pump some water uphill and then you fill a reservoir and then the water can come back downhill. So C is how much charge you store versus how much voltage there is. Or the rate of change is the rate of change of the voltage equals the rate of change of the charge, which is current. So for a resistor, current and voltage are proportional. For a capacitor, the current is the rate of change. And so we use that as filters. We use it to set the time, how fast things respond. And then you can get much larger capacitors. And so this is a supercapacitor. And these we can use to actually store energy. Batteries are more complex to charge and discharge. Capacitors, you just apply a voltage and they charge up. And so you can use a large capacitor as a kind of a short-term battery, and you can also use it to filter irregular power sources. Uh, Crystals are devices we use to tell time. And so a crystal looks like a capacitor with a thing in it, and that's literally what it is. So uh, it has a material that when you put a voltage on it, it flexes, and when it flexes, it makes a voltage, and you can push that back and forth like pushing a swing, and it can do it very precisely. And so we use that to tell time. Uh, if you make circuits with complex processors from scratch, you need a crystal. Typically, if you're using something like a Shao, the crystal is built into it. You don't need to see it. Inductors are the opposite of capacitors. You draw them like little coils. They have a magnetic field, and then they have the opposite relationship. The voltage is proportional to the rate of change of the current. Let's see, in the chat, Rico's shown an example that shows a number of different packages. And again, the packages go much smaller than what Rico is showing. I don't know if I have that. Oh, actually, I do have that here. So this was for a project. You're not going to see anything. I'm holding up a page, and this shows the smallest parts, and they're taped down. And on the video conference, you might barely see a black dot. Those are the smallest size surface mount parts you can get. Inductors are used as filters that remove high frequency. They only pass low frequency. You're likely to not need inductors. Uh, Diodes have lots of uses. You'll see diodes. So A diode, you draw a diode like this. The diode has what's called an anode and a cathode. And current can go in this direction, but it can't go in that direction. So if you plot the voltage across the diode versus the current through the diode, an ideal diode, nothing goes backwards, and it's a perfect conductor going forwards. So one of the ways you use a diode is to protect often electronic components. If you connect the battery backwards, you'll destroy the component. So you can use a diode to protect your circuit from not getting killed. And so here's an example, small diode. Um, then we use Zener and diodes and LED diodes. So um, current goes in alphabetical order. So it means there's a difference between the left and right. On a diode package, there's often a line, or on the side view, there's a facet. One side of the package looks different from the other. That side is the cathode. The way you remember it is it's alphabetical order. Current goes from the anode to the cathode. So a Zener diode it is a special kind of diode. This is voltage, this is current. What it looks like is it conducts in the forward direction, in the backward direction at a very particular voltage. Suddenly this drops. And so you can we use a Zener diode as a precise voltage reference. And then the part that you'll see a lot of is a light emitting diode. So here's an LED. So that makes light. You're surrounded by them. And so a LED is a diode. You draw it with a wiggly light coming out of it. Now, a real current voltage curve actually looks like this. It's not perfectly sharp. There's a little leakage in the reverse direction, which you can actually use as a sensor. This quadrant is where it actually makes power. That's where solar cells work. And then in the forward direction, this is the diode drop. And so like 0.6 volts is a typical value for a diode drop. So now if we connect a battery to a light emitting diode, if this is a perfect battery, the current would be infinite. And so if you do that with a good power supply, the diode will literally explode and go flying across the lab. I don't recommend doing that, but most anybody who's played with electronics at some point, either accidentally or intentionally, has done that. By the way, once again, I only see one video right now in my gallery. If you're in class, your video should be on. I want to be seeing you as well as you seeing me. So what we do is always with a diode, a light emitting diode, you have a current limiting resistor. And so remember, current is voltage over resistance. And so a typical value for this resistor might be 1 kiloohm. And so if you have 5 volts, it means it limits it to 5 milliamps, minus the change from the diode drop. So if we go to our light emitting diode, it's specified by the drop across it, how much current it can handle, the color of the light, and the angle of the light coming out. And these range, I'll talk more when we get to output devices, from little LEDs that we just use to blink to ones that are bright enough to light a room to ones that are so bright it would hurt your eye to look at it. They come in a wide range of sizes. So most common use is LEDs for indicators. Then we come to transistors, and this is one of the most important parts of the class. So there's two kinds of transistors. There's bipolar transistors, and we generally won't be using those. We're going to be using what are called MOSFET transistors. So here's an example of one of those. And this is one of the best parts in the inventory. This is 20 cents in quantity. It's about the size of a grain of rice, and it can switch up to 1.7 amps and 30 volts. And to give you a feeling, that's the amount of current going into a large machine tool in your shop. So when one of your shop machines moves a motor, this is on the order of what a pretty substantial motor is using. So many of the things I said you can do, running pumps to irrigate plants or launching cards, comes from the power of these transistors to switch loads. So the MOSFET, there's two kinds of these. There's a N MOSFET and there's a P MOSFET. An N MOSFET is a sink. So if you have a load, here's the power supply and here's ground. An N MOSFET is a sink of current. A P MOSFET is a source of current. So current goes into the NMOS, it comes out of the PMOS. One MOSFET can't do both. It can either be a sink or a source. That's hard to explain. You need this class to explain it. I'll just declare it. But it can be either a sink or a source. So the MOSFET has a gate, it has a source, and it has a drain. There's a gate, a source, and a drain. And if we go to the MOSFET data sheet, there's a key curve, this curve here. So this is the voltage between the drain and the source for the load. This is the current. And then each of these lines is varying the voltage on the gate. And the slope of this line is the resistance. And so you'll see once we get up to about 5 volts, it's pretty well turned on. Below that, it doesn't turn on all of the way. So you can think about the MOSFET. It's not quite right, but you can think about it as a variable resistor where the gate controls the resistance. You can continuously vary it. Generally, we use it all the way on or all the way off. And the reason is what's called RDS is the resistance between the drain and the source. And you want that to be small. In a minute, I'll explain, or I can explain now. Power is I squared R. So if you have a resistor and currents flowing through it, the power is the resistance times the square of the current. Generally, power, this is a problem because more power means your battery will run out faster. And a big issue is this turns into heat, and more power means your transistor will overheat, and eventually it'll either shut down if it's protected or it'll fail if it's not protected. So when let's say you want to make a motor that moves a window shade up and down, and so you need more power to it. If you have a MOSFET with a lot of resistance, you have to get rid of the heat in the circuit. So we want MOSFETs that have a low RDS, so they don't dissipate power. And we want MOSFETs with a low gate voltage, so they're easy to turn on and off. So we use what are called logic level transistors. So MOSFETs are how we switch DC loads. Then regulators, here's an example of a regulator that we use. What that does is, let's say you have your project that does something. Over here, we have a battery. And so this might be a 9-volt battery, but the processor on your circuit board typically wants 3.3 volts. And if you put on more than 3.3 volts, you'll actually kill the processor. So what a regulator does is, here, I'll make more room down here. You connect the battery in, and there's a capacitor on the output and optionally one on the input. And so this might be 9 volts and it might be varying. As the battery gets older, it might become 8 and then 7. But over here, you always get 3.3 volts or whatever the value of the regulator is. And so we use that to regulate the voltage. And then this capacitor here, this is like a flywheel or a buffer. So 1 microfarad is typical. There's a control loop in the regulator, and it needs this capacitor for sort of inertia to help buffer the charge. So regulators are how we go from a high to a low voltage. Now, a simple regulator, like I described, is inefficient. So there are DC-DC converters that can change voltage more efficiently. And again, that's harder to explain. These are beautiful parts that you may not ever encounter. These are amplifiers, and we use them to measure sensitive signals, and we also use them to produce powerful signals. So you can use that for like a microphone to measure a voice, or you can use one to drive a speaker. The reason why you might not see them is there's a lot to describe about circuits with them, but these are increasingly built into the other components that we're using. So the microcontrollers we're using, many of them have these amplifiers built right into it. And many of the microphones we use also have the amplifiers built right into them, or many of the speaker drivers. And so these are beautiful parts, but you probably won't need to use them directly. So then we come to the microcontrollers. And so in the embedded week, we saw the SHAOs, the ARMs, the AVRs. For this week, what you need to be aware of is, if you remember, there's all this stuff going on inside the processor, and we have many weeks to come to learn about it. But for today, what you need to be aware of is the pinout. So each part has a table like this that has the pinout. So this is for the SAMD. If you're using the SHAO, they have nice documentation, and there'll be tables like this. And so this is where power goes in. Oh, sorry, for the SHAO, power is coming in over USB, unless you're using the battery interface. It provides 5 and 3 volts because it has a regulator. And then there's many different functions. There's analog pins that can read a voltage. There's digital pins that can put out a logic signal or read in a logic signal. I2C is a protocol that you can use to talk between processors, and we're going to talk a lot about that. UART is a protocol you can use to talk to computers. There's power and ground. And again, think of power as the water tower feeding the pipes, and ground is the reservoir where it ends up. SPI is another protocol some parts use. QTouch is a protocol for sensing. And you'll see each pin has a set of functions it can do. And there's tables of the mapping of the pins. And often you can also reconfigure those pins. And so depending on the processor you're using, you need to pick which are the pins you want to use and for what purposes. And once again, a good guide for this week is Adrian's Fab Shao. Here he has the power and some logic pins. Here's some more logic pins. And then here he's using this for the I2C, and that's the USB. And then he shows connecting to many different devices with those. So for this week's assignment, you'll need to pick which processor you want to use and then design around its pinout. And so the RP2040 SHAO is very powerful. It has the customizable processors. The ESP32 SHAO is good for radios, Wi-Fi and Bluetooth. The ARM processors let you design a simpler circuit that can speak USB. The AVRs go down to very tiny, low-cost processors, and any of those are fine to use. Then to look ahead in the sensor week, if you scroll through, I cover all sorts of inputs, each with examples. And then in the actuator week, I cover displays, bright LEDs, video, motors, speakers, with examples to talk to them. And so all of that will be coming. So those are the components. Now we need to design circuits. So this is a Bible, dear colleagues. You should have this book out in your lab. If this book isn't handy in your lab at the electronics workbench, complain and make sure you have a copy. So we have current and voltage, and then I had explained that power is I squared R, and because I equals V over R, power is also IV, current times voltage. And then there's a couple other rules to just be aware of. One is if you have a complex circuit with many components, the sum of voltages around a circuit adds up, and all the currents into and out of a node add up, and those are called Kirchhoff's laws. So you can design all these great circuits. They can do all these amazing things. Here comes the challenge. So um, let's see, uh, this is time versus effort. Some of the things we learn are just smooth curves. Um, Today's class is going to be like climbing a mountain. You're going to have to learn a whole lot to do anything. And the reason is EDA. So EDA is electronic design automation, and this is how we design circuits. And you could use any drawing tool to make a circuit, but you would be very unhappy. And the reason is in EDA, often you start first with just sketching on paper or a tablet. Then you enter a schematic, which is what you want. What is the circuit? How are the components connected? Then you place the components to make the board. Then you need to route where the wires go. Then you might need to simulate it, and then you need to fabricate it. And there's many things that go into that. There's the number of layers in the circuit. And so we're going to talk about this is a 1D circuit. Everything is on one layer. This is 1.5D. Everything's on one layer, but I use 0 ohm resistors to cross wires. This is a circuit where I've got wires on 2 layers, on the top and the bottom. This is a circuit where I'm laying up multiple layers, and we'll talk much more about that next week. So there's the layers. You might have power planes where you fill with traces. And then a big thing you have to handle is the footprints. And I realize they don't actually say that word there. Let me. So when you place the component, if we take any of the circuits I showed you, there's the shape of the footprints. Let's see. Let me note in the chat. There's a number of things people adding. Let me add TLA to the acronyms in the chat. Does anybody know what a TLA is? If not, a TLA is a 3-letter acronym. So TLA is 3-letter acronyms. So you have to have the footprints, and then in addition to the footprints, often you have the 3D model. And so here, let me open an image. I'm going to take a minute so to add an image. So I'm going to save this locally, and then here. So this is just this weekend, there was a circuit I was working on. I'll explain the tools. And so to make the circuit, I have to route the wires. The footprints are the pads I connect to. And then I also have 3D models of the parts that let me design around it. So for all those rules, and then finally, a big thing is design rules. So once we send the board out, the vendor will have design rules for how skinny a wire can be, how close they can be together. And we're going to talk about design rules in electronics production class. And for boards you send out, you can go down to 5 mils, lines and spaces. When we make boards in-house, you need to be more conservative, so maybe 15 mils for that. And so a DRC is a design rule check to make sure you're respecting the design rules, and an ERC is an electrical rule to make sure what you did actually does what you think the circuit should do. So for all those reasons, we use specialized tools. So you could do it by hand. Raphael was a good artist. And so in this class, he did the homework, and then by hand, he drew a circuit and he machined it just by drawing it. Beautiful art. There's no design tools. There's no undo. There's no footprints. In the old days, we used to do it like this. We would have sheets where we would rub off the footprint, and we have drafting tape, and you would pull the drafting tape. And that's how we used to do it. And then you would take a picture. We don't do that anymore. Tinkercad, virtual board, fritzing. We saw versions of this for the simulation. All of these let you design circuits. The hesitation is similar to my hesitation about the CAD tools. These don't do all of the advanced functions I'm describing. So they're fine to start, but I don't recommend them. Let me then jump to what I do recommend. So KiCAD is fabulous. KiCAD isn't from, but overlaps with CERN, its history. It's freely available, cross-platform, and open source. The biggest limitation in KiCAD is it started as maybe 10 different programs that were completely separate. And they've gotten closer and closer, but they're still separate. They recently released KiCAD version 9, which is substantially updated. And so this is an example from KiCAD 8, but for the example, 8 and 9 are, there's no real important difference. So here I am in KiCAD. So this screen is a dashboard into the multiple programs that make it up. You have to tell it about the libraries. And I'm going to talk a lot about libraries. Libraries are how it knows about the parts you're using. Right now I'm showing libraries, and I'm going to talk about that in a little bit. So what the libraries do is let you look up a part, and then you can get the symbol, you can get for the schematic, you can get the footprint for the board, and you can get the 3D model for the CAD. So I'm going to do a new project in KiCAD, a simple demonstration. So then I need to make a schematic. So now it's going into all the libraries it has, and I'm going to search for a component. And so I'm going to put a processor in. So this picture doesn't look like the shape of it on the board. It's conceptually power, ground, and its connections. And this is the little 8-pin processor that we love. Okay. Then I'm going to add a resistor. And for this example, I'm not going to make a sensible circuit. And I'm going to update this to do I realize I can do a slightly more complex example. Here I'm just going to show, I'm going to connect a resistor to two pins. So now I'm wiring it up. Okay. Then I need to confirm the packages. So there I'm using a tool. These are the symbols, and like a resistor can come in many different sizes. I have to tell it which size resistor I'm using. Okay, now I'm in the PCB tool. And so this is where I lay it out physically. So this is what's called a rat's nest. These are my parts, and you'll see faint lines. The faint lines are telling me what needs to be connected. And so right now I'm rotating it because that helps untangle it. And so here what I'm doing is I'm placing components. Now I'm going to route. And route um, can range from frustrating to exhilarating. It's a puzzle. You have to figure out where the wires go. And in this case, it's pretty easy. So um, I pick a pad, and then another one lights up. It's telling me where I need to go. And then I'm starting to route it. And then one of the things KiCAD can do is you can start routing and it knows how to finish for you. So I'll start routing. Oh, let's see, that went by so fast you didn't even see it. The There's a number of shortcuts. So I'm routing that lead, and then I'm going to start routing, and I can just hit a shortcut letter, and it finishes routing it for me. Now, on the right here are all the different layers. There's copper on the top, copper on the bottom. Um, uh, Typically, the board is insulated except where the solder goes. And so there's a mask. There's a layer of the text on it, the silk screen. The edge cut layer is the mechanical layer. That's the boundary. So I'm going to set a boundary for the board. Then one of the nice features here is uh, each part has a symbol for the schematic, it has a footprint for the PCB, and it has a 3D physical model. And so right away, it can produce a 3D model of my design. That's nice for me to see what it looks like, but this is really useful for the CAD because you can take that 3D model and then design it into the project. So just in the simple toy example, I've made a PCB. Now I'm ready to fabricate. And so in-house, what I'm going to do is I'm going to produce an SVG. And here I'm telling it what parts I want to produce. So I'm going to send those files out. Then in mods, I can open the SVG. Um, that was the traces. This is the interior, and then I can fabricate that. And then I have linked here. This is a very handy extension to KiCAD, and if you want to send it, it's in the Electronics Production Week. I'll talk about JLC PCB is one of our PCB vendors. PCB Way is another one. And if you want them to commercially make a board, um, you need to upload a zip file that has all of your parts. So there's this link where you need to upload. And so you need to do a production job that exports your top, bottom, There's drill holes if you have what are called vias that I'll talk about. You have the silk screen, the masks. And so this is a really nice plugin that turns it all down to a single click. So once you have your design ready, um, you click the single button and it produces all your files for export that can then go to the board house. So that's KiCAD, freely available, cross-platform, not quite as integrated as the other tools, but very, very powerful. And it has a number of more advanced things like what's called push routing, where while you're routing, you can push other traces around the way. It can do some auto routing. Auto routing is surprisingly difficult. It's good as an assist. It's hard to do it from scratch. It's better to view routing as kind of a puzzle, as a fun puzzle. Excuse me. So yeah, hand raised, Benedict.
Hi, Neil.
Yeah.
I just have a question. Sorry.
Yep.
Okay, perfect. I have just a question. You mentioned auto routing. Do you have any experience with auto placing?
With yeah, so tools like KiCAD can auto place and auto route. The hesitation is when you're doing a giant board, it's beyond human capacity, and you really need auto routing and auto placement. On smaller boards on the size we're doing, it's a surprisingly hard problem to do well. And generally, when you let it auto route and auto place, it's a fairly messy design. You generally can beat it and do it much more concisely. So I generally don't use auto place. I do that as sort of strategy, thinking about what I'm doing, and I start routing and let it finish my routing. And so I use it as an assist. I don't usually start from scratch with it. It's a surprisingly hard problem to do well.
That's also my experience. I just want to make sure. I was curious if you have other experience or have some tools that do it better.
No, I don't. And again, on really big complex designs, it's essential. On, anything on the scope of the class, I haven't seen anything that beats using it just as an assist for you. It's continuing getting better, and in fact, KiCAD. I don't know if auto place has appeared, if there's been any update in KiCAD 9. Okay, so let me go on. KiCAD, enthusiastically recommend. Eagle has a complex history. It was a separate project. It moved into a component vendor. It then moved to Autodesk. Um, and Eagle is now built into Fusion. So what's great about that is when you're in Fusion, you have electronics design built right in. It's not a separate mode, it's fully integrated. And so you can go smoothly back and forth between the CAD and the electronics. And in fact, I should add one more link. There's a nice KiCAD plugin for FreeCAD that eases going back and forth between FreeCAD and KiCAD. But nevertheless, those are separate programs. So Eagle is freely available cross-platform. Sorry, KiCAD is freely available cross-platform. Eagle is commercial, but beautifully integrated in Fusion. And so I would recommend one of those two for this week. Altium has Circuit Maker. Then OrCAD is an industrial strength tool related to Cadence. Cadence goes all the way up to designing billion transistor integrated chips. These are open source tools for integrated circuit design. And these are projects that are beginning to make it cheaper to do your own integrated circuits. The cost for that is coming down. Let's see, there's a link to Easy EDA. I have that linked as one of these here. Again, I didn't mention it. I'm focusing on Eagle and KiCAD because that's where so much of the development and attention is. Okay, next comes libraries. We're fortunate to have Chris managing the KiCAD library. And these are all librarians. And compared to the old days, this has gotten much, much, much better. So, like, let's see, that example I showed you was using the ATtiny 3226. So if I search for that in one of these, here what it's showing me is that part is available in multiple packages. And then if I drill into it, it's got schematic symbols, it's got PCB footprints, it's got the 3D model. And these have matured. It used to be there was a lot of work to find the libraries, and you would have to add to the libraries for any non-trivial part. Now these component search engines make it very easy to find the schematic plus the PCB plus the 3D. And again, I really have enjoyed using component search engine. So over time, you're likely to build up your own personal library that you use. Again, if I go back to this link, what Chris is helpfully doing in the KiCAD Fab library is in here, he explains how to install it. You have to tell it the path to find it, and then you have the symbol library, the footprint, and the 3D. And what he's been doing a really good job is keeping up with the inventory. So pretty much most of the parts you're going to use in the class are in the Fab library, and so you don't have to worry about finding them. Over time, you may find you build your own library, but to start, you can work from the Fab library. So libraries used to be a source of a lot of pain. They've gotten much easier. Okay, next up is when you design really complex circuits, like a billion transistor processor, you don't do it at all graphically. You can't manually place a billion transistors. You do it programmatically. So Verilog and VHDL are hardware description languages for circuits. They're programs for circuits. And for many years, I I've used a hardware description language to make my circuits. And so I don't recommend this for beginners, but here's an example. So what's going on here is on the left is an editor, which by the way happens to be VI, which is ancient and which I love. On the right bottom is a terminal, and then here's an image renderer. And so what I'm going to do is rather than clicking and dragging, I'm going to I'm doing something different first. First, what I'm showing is rather than running an export job, just this hardware design, there's this PCB, here are the traces, here are the holes. It can just bottom side, here are the holes. It can directly export everything I need. And then instead of using my motor control to click and drag, what I do is I describe relationships. So I programmatically say, I want to place a resistor and align it with the crystal and the connector. and then I want wires to go between them. And so I'm describing relationships in a way you can't do just by clicking and dragging. So I've done this for so long. For many purposes, it's quicker and easier for me to describe relationships than click and drag. And I use this for circuits that are very algorithmic, where I have like repeating units or I need to do very complex placement. So those are hardware description languages. And then that inspired this project, which is, this was done by two of the Fab class gurus. This is a browser version. So in here, they took many of my examples and here, I'm going to make the window bigger. So in this version, you can click and drag from the graphical interface and pull parts in. But when you do that, you're actually updating a program over here. Or you can go to the program and you can edit the program. And so if I go to the, let's see, come back to here. If I go to the program, I can edit the program. And so I can go back and forth between a graphical interface and a hardware description, which even the most advanced traditional tools don't know how to do. So here's an article on SVG PCB, and this all just runs in a browser. And so that's very different from the traditional EDA tools, but is an option that's available. And then finally, I have linked, once you're done, like for 3D, these are sites for sharing your designs and also for selling your designs. So main goal for this week is to get you started with EDA tools. Then as the circuit gets complex, you need to model them. We saw Wokwe, which is just digital. It's not analog. I showed AVR HAS, and so this is built on Falstad. And so this, I showed you this in Embedded Week, but let me come back to, this is modeling the digital logic, but it's also modeling what the analog circuit is doing. So it's simulating the circuit. And it's based on Falstad, which is wonderful. If you go to Falstad, it's full of example circuits. So yeah, this is how a flash analog digital converter works. We'll see that in ADC week. It's full of circuits you can simulate right in the browser. The SPICE dates back decades ago to Berkeley. It's a framework for simulating circuits. And that's the most common one used industrially. There's a number of interfaces to SPICE. One is LT SPICE, one is NG SPICE. The components we're using, along with the footprint, the schematic, the 3D model, many of them also come with SPICE models that tell you how to simulate them. And then both KiCAD and Eagle know how to talk to it. So from KiCAD, you can make your schematic. Then you can go to SPICE. And now this isn't tutorial. This is very high fidelity simulation of your circuit that you can use to study its performance. And likewise, Eagle has an interface to SPICE to do high fidelity simulation. So when you're making very large complex circuits, again, before you fabricate it, it's essential to simulate it. Okay, last thing we're going to do is when you make your circuit board in 2 weeks, load your code, turn everything on, life is great, then it won't work. you're almost guaranteed to run into, well, through this class, you're going to have many, many, many occasions of circuits not working. So last thing I'll cover today is test equipment. And then you're going to see more of this in the coming weeks. So this is a regulated bench supply. Cost has come way down. These are somewhat noisy. The power isn't very clean. And I'll talk about how you measure that. But the key thing this does is you can adjust voltage and it picks the current, or you can pick current and it picks the voltage. And so, for example, if you're doing motor control, it might be that your motor works at a lower voltage or current, but it overloads at a higher one. So you can ramp this up and see how much power you're drawing and adjust it to figure out where the motor can safely operate. So this is a very important tool on your workbench. You'll make lots of use of these. These are meters and they measure voltage, current, resistance. And so one of the first things you do when your circuit doesn't work is we'll take out the multimeter and just probe it to make sure the voltages in the circuit are what they should be, like you're powering your chip. Then this is an oscilloscope. Here's a little pocket one. And there are bench ones. And these show you the signals as a function of time. And so if the voltages are right on the circuit, one of the next things we'll do is take one of these out to see the meter doesn't just shows you the average value. It doesn't show, and it may be swinging all over the place. So we use them to watch signals versus time. Then this is a logic analyzer. And what this shows you is not just simply the signals versus time, but it knows how to interpret them. And so it tells you what the signals are doing. Then you can combine these. So this, for example, is an oscilloscope, but it also knows how to do the digital signal analysis as well as the analog measurement. And then you get into these. And so this one from Salier is fairly expensive. These are a few $100s. You can find much cheaper clones of them. And what this does is it's a little module that has lots and lots of inputs. And each input can tell you analog voltages. It can tell you digital logic. And it knows all of the different protocols that we use. And so it knows how to interpret them and decode them for you. So I mentioned I2C. And so when you talk to an I2C device, it may not be working and you may be sending the wrong commands to it. You may misunderstand the commands it's sending back to you. And so these logic analyzers are essential to debug that. And again, thanks to our friends in Shenzhen, the Sally is a few $100s, and you can get these crazy ones for like here's one for $12, and these work. They're quite usable. Um, uh, and then finally, this isn't a very active project, but I have it here because I really love this project. This is looking at how to measure almost anything, meaning using Fab Labs to make Fab Lab tools. So making meters and oscilloscopes right in the lab. So group assignment. In your lab are all these tools. I want you to use the test equipment to look at a microcontroller. So if we take Adrian's Fab Shao, USB data is going here. I2C data is going here. He's got, there's various voltages on the shell. What I want you to do is use a DVM to probe the voltages. Use an oscilloscope, for example, to look at the noise on the power supply. And then use a logic analyzer to decode the protocol. So you can actually look at the USB commands and actually see what's going on inside USB. So in coming weeks, you're going to need that for debugging. This week, I want you to learn to use your test equipment. Then individual assignment, let's see. Yeah, I didn't mention a function generator. So there's the reason is these devices put out waveforms, and historically these were important in various ways in test equipment. The reason I didn't mention a function generator is in general now it's so easy to program the processors we're using to produce whatever we want that it's been years since I've used a standalone function generator. I just program a processor to produce whatever output I want. Okay, so I want you to use an EDA tool. So a full-blown one of the options. And again, if you're not sure, I recommend KiCAD as freely available cross-platform. If you're already in Fusion and happy, then you've got Eagle built right in. I want you to design a development board, meaning it has a processor and it's designed to interface to think ahead to the devices you're going to be using. Go through all of the input and output devices we're going to be covering. And I want you to have be able to interface to them. And then I want it to be able to communicate. So depending on what you use, it could be USB, it could be looking ahead, it could be Wi-Fi, depending on the part you use, and design it. I'll make a note, one extra credit is simulate it. One is try more than one design workflow, compare the workflows. One extra credit is design a case for it. Which means you have to export your design into a CAD environment and then be prepared for in 2 weeks, we're going to actually produce it. So this doesn't need to be the final circuit board for your final project, but it should be something that lines up with your final project. Something that lets you learn about the processor you'll be using and lets you start working with the interfaces you'll be using to it. But the main goal for this week is to get you going with an EDA tool. And to start, you'll be frustrated. It's harder to do this with the EDA tool, but it brings discipline. It forces you to be able to, you have to be able to be hierarchical and parametric in the traces. You have to be able to use the footprints and the all of the parts from the libraries. And so it's worth the learning curve to learn these tools to then get all of the support you get for them. Okay. So this begins the journey of electronics design. In 2 weeks, we'll build them, and then in future weeks, we'll learn much more about the inputs and outputs and networks. Keep up with your weekly sites. Keep up with your final project site. Start the final project site if you don't have it. And begin looking ahead. When we get up to the midterm, you should have all met your global instructors already. If you haven't, right away you need to schedule a meeting of student, local, and global instructor. And then at the midterm week, your assignments up to then will be due. So don't leave work behind you need to catch up on. You need to be caught up on it by the time we get up to that. And with all of that, happy electronics designing. And for any questions about anything, you have the Saturday team. See you in a week. Bye-bye.
Adiós.
Bye.
Muchas gracias a
Bye.
todos.
Goodbye.
Vamos. Chao.
Bye.
Adiós, nos vemos.